Hello, I'm Doug, Stand-Up Physicist. This is the third show of 6 trying to recreate my talks on unifying gravity and electromagnetism by analogies to electromagnetism. I gave these talks in 2003 to a small crowd. Today's topic is fields. And we're actually going to make television history in this discussion. How so? Well, in the entire history of television, I don't think there was ever a show that had as many partial differential equations as the following. What is a partial differential equation? Well, it's a tool of calculus. And people don't usually write out many of these tools, many of these partial derivatives. Why? Well, first of all, it scares people. But the other reason is that it's actually kind of hard to typeset them, to write them out in a neat way. As a matter of fact, it used to have to be all done by hand, and so they really limited the number of equations. But then somebody developed a wonderful way to write equations out really neatly using something called tech and later on LaTeX. But that even took a little bit of work to kind of get out. But once you did, the equations were really looked good. And people just don't like to write out every little line explicitly. I always found it frustrating when someone said, well, you take this and you get to that as an exercise. The reason I didn't like that very often was because often I couldn't do the exercise. It was too difficult for me. I can follow along. Okay. But they didn't spell out every step because it took too much work to typeset it. Well, in 2003, I was completely, utterly unemployed. Hard to believe, huh? Why wouldn't somebody want an amateur theoretical physicist? Oh, let's not go over the reasons. But I was preparing for this lecture. And I wrote out this one equation. And I said, well, and then you get to there, the way it's normally done. And I said, you know, it'd be better if I said, I start here, and then in the next step I do this, and then the next step I do this, and then I end up with my result. That'd be great if it was all spelled out with words and equations. And I did it. It just took a full-time job that I wasn't compensated for. But it worked. So that's what's going to be the basis of this little show, and we will have more differential equations than any other show in television. So what are these things called? Fields. Well, I think of fields as being the choreographers of atoms. They tell them where to go when. Now, if this duck was an atom, and it was kind of moving around pretty randomly like this, this would be thermodynamics. But that's not what we're going to be doing today. We're going to be doing eloquent fields. You may have seen pictures of like iron filings and they make these cool figure eights and stuff like that. Those are the types of field equations we're going for. I'm going to introduce you to all the players, because it quickly can be confusing as to what is what. I am then going to introduce the Eulerlagrange equation, a wonderful equation from the 1800s that allows you to start from a Lagrange density. Remember, that's a function that only kind of gives you back one number, but it's a summary of all the energy interactions that can happen inside a box. the Euler-Lagrange equations tell you how to start from that and then get the field equations every time. I will then introduce fields, which is how the potential actually changes. That would be average Joe and the deviance, if you remember that from the tensor show. And then we will look at those fields in detail to look at all the little component parts. And then we will look at field equations. Field equations are how the fields kind of change in time. So who are the players? Well, we start with the Lagrange density. That's that single number, a scalar, a rank 0 tensor that describes every energy interaction that can happen inside of a box. The field equations are rank 1. And these are actually the changes in the changes of the potential. There are several different ways to write the same darn thing. There's the Euler-Lagrange equation, which looks kind of scary. Then there is this four-dimensional field equation. And then there is writing these four-dimensional field equation as product of a bunch of things having to do with the fields themselves. Then there are the fields. Fields are rank 2. They are the changes in the potential. The stuff that makes up electromagnetism is the antisymmetric tensor. And so that is the deviance. And I am going to introduce actually 3 new fields to try and explain how gravity works. And this really is my own work, and you can't find it in any book. It's not published yet. Could be wrong. I hope not. But you'll be able to see how that's the average Joe stuff. So average Joe and the deviance make up all the ways that a potential can change. That's all the rank 2 tensor stuff. Now you get introduced to the principle of least action. The reason we do this is that this is going to lead to how to generate field equations. The principle of least action I actually prefer to call the principle of the couch potato. As you know, couch potatoes don't like to change for anything. I mean, sometimes if a show is really weird, they might, get out the old clicker and, change some things. But other than that, couch potato is going to stay there. So what we do is we start with what's called the action. And the action is we take that Lagrange density, which is everything that can happen per unit volume, and we integrate that, add up everything that can happen inside a volume, and also over time. See, if we just integrate it over volume, we just get back, this is all the energy that's there. But now we're saying this is all of the energy that's there over a period of time. And as you might imagine, well, that number could grow. But remember the couch potato. The goal is to find out how we could change this Lagrange density in such a way that when we came back at and integrated over a longer period of time, it actually wouldn't change at all. So what we're going to do is what's called the calculus of variations. This doesn't come up in high school classes. You can go through college and not come across it. It's too bad because it's a wonderful idea. The idea in calculus, in what's called integral calculus, usually what you do is you add up, and you end up with just a number. And with the calculation of variations, what you do is you add things up but you end up with a function. And a function then gives you a number. So it's a little bit more abstract, but a very powerful tool. So now we're going to derive the Euler-Lagrange equations explicitly. Everything's going to be written out. I don't know if you can find a book where it's written out as much as it's going to be done in this very show. So we start with the Lagrange density. And it should be a function of both the potential and a change in the potential. Now we form the action, and the action is simply the integral of that Lagrange density with respect to volume. So add up all the volume slices and time. But then what we do is we say we are going to vary this action. We are going to vary this action with respect to the potential and to the changes in the potential. And that's very good. And so let's write that all out. And actually, I should say this. We're going to do that and hope to find something where that variation actually equals 0. That's the couch potato principle. We do the variation with respect to, by taking the derivative of the Lagrangian with respect to the potential and taking the derivative of the Lagrangian with respect to the change in potential. Now, it'd be really nice if somehow we could rewrite this. Rewrite it so that it was all expressed in terms of the change in potential. So what we do is use something called the chain rule. And that allows us to express everything as the variation in the potential. But it actually has an extra term, so we have to subtract something away from that to make it work out. And then there's this theorem of Gauss that I actually don't understand so well myself. But it says that that term in the middle there, if you integrate it over this volume over time, it actually will equal 0. Then what happens is we say, okay, now we've got these two terms, and they both depend on how we vary the potential. So we would know that this thing would always equal 0 if those two terms were equal to each other. And so that's actually the entire statement of the Euler-Lagrange equation. That you will find a couch potato minimum if it turns out that when you take the derivative of the Lagrange density with respect to the potential, and that equals the derivative of the Lagrange density with respect to the change in the potential. And that all has to equal 0. It will always equal 0 if those two are equal. It's guaranteed. It's guaranteed! Like those Ginsu knives. All right. Now, though, that's kind of abstract. We're going to now apply it. So now let's write out the Euler-Lagrange equations. Let's start with that, without any indices. So we write down all the parts, bar none. You can't find a book where this is done. The entire collection is there. So you can stop the video, if you're taping this, you can stop right there. Actually, these notes are available online. And the only conceivable way to really understand this is to do it yourself and go ahead and use those notes to help yourself get through it. And now we have to write out that gem Lagrange density from the last show without indices. So we write out each and every one of those components. And you'll see it's got several things. It's got some charges in there. And the charges are multiplied by things like the parts of the potential. You see phi in there, and a's, x, a, y, a, z. Remember, in the Euler-Lagrange formula, we take derivatives of this thing with respect to phi. with respect to AX, with respect to AY, AZ. So when we do that, we're going to get back those charges. And there are things like d phi dt, d phi dx, etc., etc. And we actually take derivatives with respect to d phi dt, with respect to d phi dx, etc. But what makes it simple is that these are all just squared. And if you remember this from calculus, you take that 2 down, and you subtract 2 from that, and you get 1. So you have a d phi dt, d phi dx, etc., etc. You just got to get all the minus signs and plus signs right. Okay, well, if you now apply the Euler-Lagrange equations to the gem-Lagrange density, what you end up with is on this slide here. You end up with a bunch of terms, and what's really amazing is that there's a simple summary of this whole thing, that it's just one current density, the electric current density, minus the mass current density is equal to a 4-dimensional wave equation. If a physicist sees this, he'll immediately say, well, that looks familiar. It looks like the the Maxwell equations in the Lorentz gauge. But this isn't quite like that. It's not quite like that because it has that other current density. We need that current density for gravity. We need that it's a minus sign. Why? Because that minus sign means that like charges attract for gravity, but for EM, like charges repel. And if you were to look at that Lagrangian from a little short time ago, there was no fixing of the gauge. So we aren't doing the Maxwell equations in the Lorentz gauge. We're doing something fundamentally different. But it's also relatively easy compared to what physicists usually do with Lagrangians. Trust me. What are fields? Fields are how potentials change. It's that second rank tensor. It's the derivative of the potential. It's an asymmetric tensor. But we're going to divide it into a bunch of different parts. Because nature appears to do that, because they transform differently, is the technical reason. There is the stuff that makes up the antisymmetric tensor, the deviance kind of tensor. That would be the electric field E and the magnetic field B. And you will find them in any book you pick up on electromagnetism. I am introducing 3 new fields. 2 of them are analogs to big E and big B. So I call them small e and small b. So I don't get too confused. Because the idea is that if our wave is moving along this way, that we have some transverse modes that do the E and B thing, and we have a longitudinal mode that does the small e, small b thing, and there's a scalar mode that does the stuff along the diagonal. Because stuff on the diagonal is in a symmetric tensor, but it is not in an asymmetric tensor like the one for electromagnetism. So there are 16 fields all told. Let's look at this in detail. So the asymmetric tensor basically has d phis, dt's, dA's, dx's, all over the place. There's no real pattern here. We can build a pattern by splitting this into two, into an asymmetric tensor, antisymmetric tensor and a symmetric tensor. The antisymmetric tensor is the deviance, and it's the stuff of EM. And the symmetric tensor is the stuff of gravity. And if you put these all together, you see all the E's, both big E for EM and big B, and the small e, small b, and small g for gravity. We move on to those field equations. Field equations are how the particles move, and they are actually the changes in the fields. So it's actually the changes in the changes of the potential. There is Gauss's law for electromagnetism, and we can use that law to actually figure out how to write the field equation in terms of E, B, and G. And the method is to take your EM law to add in analog terms and add in a term that would be along the diagonal. So Gauss's law is the electric density equals the divergence of the electric field. And so what we do is we now have the mass current density, which we of course had to subtract so that things work out. And we take the divergence of the small e field, and then we take the time derivative of that g component, that thing along the diagonal. And you can work out explicitly, it's right there, and show that with this definition for what the fields are, if you now write them in terms of A's and P's and whatnot, we really do end up with the field equations. We really end up with time squared, the second time derivative minus del squared acting on phi really is equal to the current density. So it's really just another way of writing exactly the same thing. It's kind of more comforting though, because people actually make E field meters and B field meters, and in some ways a scale is actually a small e field meter. I think I'm right on that. Okay, so there's another really important law out there, and that would be Ampere's law. And so we use exactly the same approach. We add one half of the EM law plus the symmetric analog, and we add some terms along the diagonal, and that should be the new law. That should be consistent with the field equations that we've already derived earlier by applying the Euler-Lagrange equation to the gem Lagrange density. And believe me, it's a bit of math, more math than you'll ever see on the cooking channel. But it really does work out. At least I was really quite amazed when it did. But it's one of those things that make me believe that this is not a delusion, or if it is, it's quite an amazing one. Now, let's look at those things called vector identities. Well, as the name implies, they're identities. What that kind of says is that because of the way we define things, we just know they're going to be true. So, because we define the magnetic field in a certain way, we know that it's necessarily the case that there are going to be no magnetic monopoles. And because of the way we defined the electric field, we know that Faraday's law is going to hold. That's still true. It's an identity. Can't get around it. You got to know who you are. I'm the stand-up physicist. I don't know what that means. Now, there aren't these sorts of identities for the fields of E, small b, and small g. I'm sure that means something, but right now I don't know exactly what it means. Well, I hope you've enjoyed this introduction to fields and field equations. Thank you very much.
All the girls in the classroom think he's hot. He shows up wearing the sandals with the white socks. He hears them giggling while he's got his back to the class. He thinks he's got an eraser mark on his ass. And all the girls from the hall show up to hear him talk, even though most of the time he's covered in chalk. Math prof, rock star. Math prof, rock star. Oh yeah. Math prof, rock star. He was young, he never thought that he would be a math prof, rock star. And after hours outside of his office, there's a line waiting, full of girls who want to ask about their quadratic equations. She leans over the desk and twirls a pencil in her hair, complains the grade he gave her was way unfair. And all the professors, they laugh about it and they wish him well. The guys in the class are all just jealous as hell. Math prof, rock star.
Hello, I'm Doug, stand-up physicist for dogs. Today I'm going to explain my unified field theory to Mona. She understands light. She appreciates that 50,000 years ago, a couple of hydrogen atoms fused in the sun and took 50,000 years to get to the surface, and then 8 minutes to get from the surface to Earth to bounce off this, this tennis ball and go right into her eye. And the other thing about a unified field theory is gravity. And that she understands. She can track this ball, but she may not yet realize, do you realize that it's due to a 4-dimensional wave equation? That there's this diffeomorphism between the potential and the metric? Do you appreciate that? Oh, that's beautiful. Oh yes, thank you. You like that. She likes this kind of theory. Okay. Whoa, 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 let's go get it.